Scientists, today we are going to be talking about planetary motion. So we kind of established the sun as the center of our solar system, and all of the planets and asteroids and comets and all these other things that we talked about orbiting the sun, held in place by the sun's gravity, or held in orbit, I should say, by the sun's gravity. And today we're going to get into a little bit more detail about how that happens. So we're going to talk about early models of the solar system. We didn't always know everything we know now about the solar system, and we're constantly learning more things. But kind of tracing through a history of what we knew about the solar system, or what we thought we knew about the solar system, is an interesting way to kind of see how our understanding has developed over time. We'll talk about Johannes Kepler and his three laws of planetary motion. We'll talk about Isaac Newton's law of universal gravitation, and we'll talk about gravity and inertia and the balance that they have keeping planets in orbit around the sun. So in the solar system, right, every planet revolves, orbits the sun in the same direction. They all are moving in the same way. They're not moving opposite one another at any point. A planet's orbital period is the time it takes for the planet to make one full orbit around the sun. So if you start in one spot, the furthest spot from the sun, if you're in your orbit, because we know orbits are in an ellipse shape, like this oval shape. Let's say you were at the furthest spot from the sun. How long does it take you to go one complete orbit around and get back to that furthest spot once again? And we would refer to that as a year, right? We know that it takes a year on Earth, 365 and a teensy bit extra, to go one full orbit around the sun. And so sometimes you'll hear people referring to things as like one Earth year, or one Mars year, or one Jupiter year. And what they're really trying to say when they say that is how long it takes Mars or Jupiter or whatever to make one complete orbital period. However, this was not always the case. Up to and even through most of the Middle Ages, people believed that Earth was the center of the universe. And that was called, now, they didn't have a name for it then, but now we call that the geocentric model. Geo meaning Earth, centric meaning center, so geocentric meaning Earth at the center. And it was not until the 1500s, really, that Nicholas Copernicus, who was a Polish astronomer, questioned this geocentric model. Excuse me. And he wasn't the first one to question it, but he was the first one to really posit some good mathematics behind an alternative model. Because up until Copernicus, all the alternative models were more convoluted and more complicated than the geocentric model itself. Copernicus suggested a heliocentric model of our solar system. Helios meaning sun, centric meaning center, obviously heliocentric, sun-centered model of our solar system, all the planets orbiting the sun. And he thought that all the planets revolved around the sun in the same direction, so he got that much right. And he thought they all went in circular orbits, which is almost true. They are not perfect circles. They are off a little bit, but he was pretty darn close. And he also thought that each planet took a different amount of time to orbit the sun. So he started to posit that every planet had a different orbital period, the length of 1 year, as it were, on each planet was different. And Copernicus was correct in most of these assumptions. He got it 95% correct, which is pretty amazing considering he was coming from a place of not really knowing much at all. Um, he was incorrect about the shape of the orbits, as we mentioned, right? He thought they were perfect circles, when rather they are not. They are ellipses, like these oval shapes. But everything else he said was pretty much accurate. Here is a picture of Copernicus, and he is holding a heliocentric, a scepter, I guess it is, with a heliocentric model. Here's the sun, and you can see the various planets. I believe that's Earth and Earth's moon, indicating it's orbiting the sun. He's also holding a pair of compasses in his hand, which are used to draw perfect circles, indicating that he believed that the path of every planet around the sun was a circle, which was pretty much the one thing he got wrong. And this is a photostat of one of his drawings, and you can see, right, we've got the sun, we've got Mercury, Venus, we've got Earth with its moon, and Mars, Jupiter, Saturn, and then there wasn't a distinction between Uranus and Neptune. They hadn't quite been discovered yet, so out at the edge of our solar system. So this is what he believed our solar system looked like, and we'll see how this is certainly a much better model than the geocentric model, but it doesn't quite give us the full picture, as again we'll see in a second. And then about 100 years after Copernicus, a German mathematician named Johannes Kepler was able to demonstrate that every planet orbits the sun in a closed curve known as an ellipse rather than a circle. And there's actually a pretty precise mathematical definition of an ellipse. A circle is the set of all points equidistant from one single point. So if you draw a dot, if you put a dot on your paper, and then you want to draw every single point that is exactly 1 inch away from that dot, well, you would draw, like there would be, maybe I can do this with a pen. Let's see. Yeah, here's my dot. And I want to draw every single point that's 1 inch away from that dot. Well, here's 1 inch. Here's 1 inch. Here's 1 inch. Here's 1 inch. And also here, 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 and also here. And you can see that the set of all points that is exactly 1 inch away is a circle, right? I would eventually draw enough dots that I would get, and I'm going to try and do this with my mouse, so it's not going to look very nice. But you get the idea. We get a perfect circle. An ellipse is the set of points whose sum is equidistant from 2 points, 2 foci, or focuses, 2 foci. So instead of one central point in a circle, we have 2 foci. And let's say I want the sum of these things to be, I don't know, 1 inch. So it could be a half an inch from each one of them. Could be an inch here, half inch from each. You get the idea, and you start to see, as we draw this ellipse or this oval shape develop instead of a circle. And it's not, and again, I'm sorry, I'm trying to draw with a mouse instead of on an actual board, but that's the idea. I know that's not a great picture, but I think you get the point. It's not terrible to describe it as a stretched out circle or a squashed circle, because that's essentially what it is. Instead of a single focus, an ellipse has 2 foci, which is the path that all planets take around the sun, with the sun as one of the foci. And it's that discovery that, again, Johannes Kepler posited back in the 1600s that is called Kepler's first law. Kepler's first law: planets travel around the sun in an ellipse shape. Unlike a circle, which is a single point at the center, as I just described, an ellipse is like an oval, and it's not really an oval shape, because an oval is kind of an ill-defined term. But it has two centers or two foci, which is the plural of the word focus. Here's maybe a slightly better image, and again, you can see the sum of any point on this ellipse is, or any point on this ellipse has the same distance from both foci as like a sum. So like this, I'm sorry, this is terrible, plus this is the same as this, plus this is the same as this, plus this, and so on and so forth. I think we get the idea. Anyway, the sun is one of the foci, and the planets orbit the sun, and that is why in Earth's path around the sun, there are times of the year where we are slightly closer to the sun, right? This is an exaggerated image, right? It's not this, we do not get this close to the sun and this far away from the sun. But, so this is exaggerated. But there are periods of the year where we are closer to the sun, and there are periods where we are farther from the sun. Although every planet's orbit is different in size and different in shape, the sun is one of the foci in every planet's orbit. The other one is not the same. It's somewhere else. We call the semi-major axis the average distance between the sun and a planet in its own orbit. And it's important to note that because planets have elliptical orbits, they are not always the same distance from the sun. We refer to the point where a planet is furthest from the sun in its orbit, we call that aphelion. And the point where it's closest, we call it perihelion. Oh, there you go, great. Again, super exaggerated. This, it's not this elliptical. It's much more circular than this. But there are points where Earth is closer, and the closest Earth gets to the sun we call perihelion. And there are points where it is further from the sun, and the point where it's the farthest we call aphelion. Furthest away, And we had the same idea when we talked about Earth and its moon. We talked about there are points in the moon's orbit where it's closest and where it's furthest, and we called those apogee and perigee. So apogee and aphelion, perigee, perihelion. You get the idea. Let's just talk about Kepler's second and third laws in one slide. He also discovered that planets move faster when they're closer to the sun and slower when they are farther away, which is his second law, essentially. He found this fascinating idea that if you draw an imaginary line between the sun and a planet, that planet in its orbit will sweep out equal areas in an elliptical orbit in equal periods of time. So I'll show you a diagram that'll make this make more sense in just a second. But that is Kepler's second law. And his third law is a mathematical relationship between the size of a planet's ellipse and its orbital period. But it's a little complicated and a little beyond the scope of what we need to discuss in this class. But the second law is kind of important to understand. So imagine we have this planet, planet A. Let's say it's Earth. Planet A moves from point A to point B. Earth moves from point A to point B in the course of 30 days. Well, this imaginary line between Earth and the sun sweeps out an area. So this checkerboard region, right? And we can kind of do like the old school count the boxes kind of method, right? Like 1, 2, 3, 4, 5, 6, 7, 8. And we can see what the area of this region is. Well, what Kepler's second law says is that if Earth moves from point A to point B in 30 days. It moves quicker because it's closer to the sun, but as it gets further from the sun, it gradually moves slower and slower and slower, so that over the same period of time, over the same 30 days, Earth would only move from point H to point I, less physical distance, right? A to B is pretty far. H to I is pretty short. But what Kepler notes is that the areas are the same. This purple triangle, which is not really a triangle because it's two sides and a curve, but this purple triangle has the same area as this white triangle. And if we counted the boxes as best we could, we would see those be perfectly equal to one another. And it is the case for all of them, right? This area here in between I and J in the sun, this area between JK and the sun, and so on, all of those areas are equal. There's a note up here that says this law is just a consequence of the law of conservation of angular momentum, which is a wonderful thing you'll talk about when you take physics eventually. But for now, this helps us describe planetary motion. We are actually moving faster when we are closer to the sun, and we are moving slower when we are further from the sun. Kepler made a ton of amazing discoveries, and his second law really, first and second law, right? The fact that all planets orbit in this elliptical shape and that they do so with this equal area law, amazing discoveries. But he wasn't really able to explain what made the planets that are closer to the sun move faster than the ones farther from the sun, or even just a single planet, when it is closer to the sun, moves faster than when it is further. And he couldn't explain that. But again, maybe 50 years later, during the late 1600s, Isaac Newton, who was an English scientist, he came up with the answer. And Newton didn't understand what caused gravity. But we often attribute the discovery of gravity to Isaac Newton. There's this famous, probably apocryphal tale of him sitting underneath an apple tree and an apple hitting him on the head, and he goes, "Oh, eureka, gravity!" Right? Like, and he understands that. But he, for lack of a better way of describing it, discovered gravity, or at least came up with the theory of gravity. And again, he didn't know what caused it, but he was able to use his understanding of it to explain the forces of attraction between two objects. This is a picture of Newton. Got that 1600s hair. Newton developed this theory that small objects fall towards Earth because the two objects are attracted to one another by gravity. It is not just that the Earth pulls everything towards it. It is that any two objects are pulled towards one another by gravity. And it's simply the fact that Earth is so large relative to everything else that everything seems to get pulled towards Earth. But if you take a pen in your hand and you drop it, it flies towards Earth, and that's because Earth is pulling the pen towards it, but the pen is also pulling Earth towards it, right? You just don't notice it because the Earth is so massive. It exerts much more. The movement of the pen is much more apparent. So all two objects, or any two objects, are attracted to one another by gravity. And Newton realized that the strength of gravitational force depended on two things: mass and distance. So gravitational force is a function of mass and distance. For example, if two objects are moved twice as far apart, the attraction between them will decrease by a factor of 4. It's actually a function of the square of the distance. So the fact that you are standing on Earth's surface, if you were to go up, 30 miles into space, you would feel less gravitational pull. Not no gravitational pull. you'd feel significantly less gravitational pull because you are further from the center of Earth. And similarly, if the mass of one object doubles, the gravitation between the gravitational attraction between them doubles. It is a function of mass, and primarily because Earth is just so massive. It is the most massive thing on Earth because it is Earth. Um, it kind of dominates the gravity. Uh, Again, it's a little bit overly simplifying things, but that's the essence of it. So the reason planets orbit the sun rather than just crashing into it, right? So we're talking about mass being, gravity being a function of mass. And so the sun is by far the most massive thing in our solar system, right? It is orders of magnitude larger than even the largest planet, Jupiter. We so like thousands of Earths could fit inside the sun. Tens of, maybe even hundreds of thousands of Earths, right? I can't remember the exact number, but the sun is just so much larger. So why is it then, if gravity depends on mass and the sun is so massive, why isn't everything in our solar system just pulled straight into the sun? And Newton realized that it was inertia that helps keep this from happening. Inertia is one of Newton's famous laws, that an object at rest tends to remain at rest, and an object in motion tends to remain in motion. So the idea that if I, like I have right now, a can of seltzer sitting on my desk beside my computer, that can of seltzer is an object at rest, and it is going to remain at rest unless acted on by an outside force, unless I bump into it or the wind blows through the window or something and knocks it over. That can of seltzer is at rest, and it is not going to start moving unless something causes it to start moving. Likewise, something that is moving is not going to stop moving unless something causes it to stop. And that one is a little bit hard. When I described my seltzer can sitting on my desk, you all said, duh, of course, chef, like your seltzer's not going to go anywhere. We all understand kind of the first part. An object at rest remains at rest. Second part, a little harder for us to understand because that's not always our experience. When we see an object in motion, it doesn't usually stay in motion, right? If I take a baseball and I throw it, it doesn't just keep going forever. But Newton posited that it would. And the fact that baseball eventually stops and lands on the ground is because it's being acted on by outside forces like wind resistance, like gravity. All of these things act on that object in motion to cause it to stop. However, if you were in the middle of deep space, far from any object, you took a baseball and you threw it in a frictionless vacuum and where there's no other forces, that baseball would indeed continue to travel forever and ever. It would not stop until something caused it to stop. And so this inertia is what balances the gravitational pull between the sun and the planet. The planets are moving really, really quickly through space. Again, like it only takes, I know it sounds like a long time, it only takes 1 year for the Earth to travel all the way around the sun in the giant elliptical path it travels. If it weren't being pulled by the sun's gravity, the Earth would just fly off into space in a straight line, right? Just like that imaginary baseball I was talking about. It would just travel in a straight line forever and never stop. However, because of the sun's gravity, the planets travel in these curved elliptical paths. Likewise, if it were not for inertia, the planets would just all get pulled right into the sun. But because of inertia, we have these curved paths. Again, think of it as like a tug of war, but not really. They're not pulling in opposite directions. But they are pulling at an angle to another. The path that Earth takes around the sun is a constant balance between the gravity between the Earth and the Sun, pulling these two things together, and the Sun trying to pull Earth this way, and the inertia that the Earth has, traveling as fast as it does, trying to send it off in a straight line this way. And those two things balance, and the Earth travels in this curved path, which is the path of the ecliptic, right? The elliptical path that the Earth takes around the Sun. I hope that was manageable. Again, this is not a perfect lesson to do without being face to face together and me being able to kind of draw you some better pictures and show you some things. But I hope that all made sense. Please try the next page of your packet for homework, and I will be in touch with you soon. Have a great day, guys, and I'll talk to you soon.